Hello ladies and gentlemen, welcome to our third session on limit. So suppose that we are given a problem like this, limit into 1 plus 1 over n all raised to the power n when n reaches infinity. But before we solve this, we have to recognize that this is actually an intermediate form of 1 raised to the power infinity. So we are going to let f of n to be equals to the limit of n approaching infinity of 1 plus 1 over n all raised to the power n. So how can we solve for this n? So for us to solve for this n, we have to use a log process. So we know that the ln of x raised to the power y is actually y ln x. So meaning that this n will actually come here when we have a ln. So this will be equals to, I'm going to introduce ln on both sides of the equation. So we are going to have ln of f of n, which is equals to limit of n approaching infinity of ln of 1 over n raised to the power n. So this n will actually come somewhere here and multiply ln. So we are going to have limit of n approaching infinity of n multiplying ln into 1 plus 1 over n. That's what we are going to have. So now, how can we rewrite this function in such a way that we don't affect this n? So this is the same as limit of n approaching infinity of ln of into 1 plus 1 over n all over 1 over n. Because of if we multiply the numerator and the denominator by n, we are going to get the original equation. So now we are going to use L'Hopital. So in order for us to use L'Hopital, we can see that this ln is a function, but inside this function we have a nested function of 1 plus 1 over n. So we are going to use what is known as a chain rule. So a chain rule says that if we are having a function of f and then inside nested the function of g of x, so we are going to differentiate f as a whole. Then after that we are going to multiply by the prime of the nested function. We are going to multiply by the prime of the function nested inside the original function of f. So now let me erase this part here. So using this we can see that the limit, but don't forget that ln of f of n is actually equals to the limit of n approaching infinity of ln of 1 plus 1 over n all over what? 1 over n. And we are going to use L'Hopital. We are going to differentiate this and also differentiate that. So we can see that the limit of n approaching infinity is going to be the differentiation of the function of ln, which will be 1 over 1 plus 1 over n. I've already differentiated it, multiplied by the prime or the gradient of the nested function, which is, so our ln actually is actually f of g of x, and then we have already differentiated. We have already differentiated this. We need to differentiate this one, g of x now. So we are going to divide by what? The differentiation of 1 over n squared. But we know that 1 over n is actually the same as n minus 1. And this is the same as n minus 1 minus 1 and minus 2 here, which will be the same as minus 2 over n squared if we are using the positive exponents. So it means that even here we are going to have minus 2 over n squared. So now let me erase the last part. So now check. Ln of f of n is equals to what? Is equals to the limit of n approaching infinity of 1 over 1 plus 1 over n multiplied by what? Multiplied by the differentiation of the function inside the brackets. So if we differentiate a constant of 1, the answer will give us 0 here. And then when we differentiate this, we already saw that we are going to get minus 2 over n squared. We are going to get something like this. But this is divided by minus 2 over n squared. So 0 minus 2 over n squared is the same as minus 2 over n squared. So this will cancel out in this one. So we are going to have a ln of f of n, which will be the limit of n approaching infinity of 1 over 1 plus 1 over n. We are going to have something like this. Now, we need to use the laws of limit to distribute the limit. So, we said that ln of f of n is equals to what? We are going to distribute this limit inside the bracket. So we are going to have the limit of n approaching infinity of 1 all over the limit of n approaching infinity of 1 plus the limit of n approaching infinity of 1 over n. So now listen very carefully, because that's where most of the people makes the mistake here. So, but we already said that the limit of x approaching infinity of 1 over x to the power n, it doesn't matter the value of n, this will always give us 0, provided that n actually lies between negative infinity all the way to negative infinity. So, I mean negative infinity all the way to positive infinity. So we can see that this case is actually the same as that one. So we are going to have ln of f of n equals to, the limit of constant is just constant, and even here is just 1 plus, but this one will go to 0. So it's 1 over 1, which is just 1. So, but we are not solving for ln of f of n. We are actually solving the ln of, we are actually solving f of n, not the ln of f of n. So, for f of n will be equals to Euler constant raised to the power 1. And this is equals to the limit of n approaching infinity of 1 plus 1 over n raised to the power 1. So this brings us to the end of our session. So if you like this session, please like, share and subscribe. Hopefully we'll see you on the next session. Thank you.